Finally, in the end, they went off down the road to some theoreticians who were actually interested in this kind of thing and said, what the hell is that? And the theoreticians said, well, don't get rid of that, whatever you do. That's the echo of the Big Bang. So they had finally, literally tripped across this thing. They had found exactly the right temperature, exactly the right sort of features. They had found the echo of the Big Bang. And that sort of marks a very important watershed. We said in 1929, we discovered that galaxies were moving apart. That was one thing. But in 1964, we had the first really uncontestable evidence. This means the Big Bang really happened. Because that radiation can't have come from anywhere else. By definition, when you measure it, it's everywhere. There simply is no other rational explanation. Unless you think maybe there's an alien universe. You know, whatever about an alien planet, I've never heard of an alien universe responsible for it. So it seems pretty watertight. So that's pretty much the end of our talk. Let's just quickly look, before we do questions and answers, let's just quickly look at what's been discovered in recent years. That was in the 1960s. What's been happening since? Well, the answer is two things. First of all, we've started building satellite telescopes. Anybody know why? Why would you put a telescope in a satellite? Much more expensive. Somebody had it there, the what? See further out, you have partly, but somebody else said something there? The atmosphere. The reason is the Earth's atmosphere gets in the way. If you're trying to measure things and you've got loads of clouds and basic summit and all that, it all gets in the way. Whereas if you can put your telescope way out there in space, literally further out than the moon, well then you'll get a much, much better measurement of what's going on in space because you won't have any interference. And the first thing they discovered in 1992 was, yes, they got a cosmic background radiation signal, but this time, look at the spectrum. That's a picture, more or less, of what it looks like. They get a full spectrum of what it looks like. They made very, very accurate measurements of that, and they found it is exactly what's predicted by inflation. And those guys actually, just this time last year, this month last year, those guys got the Nobel Prize for that at last. That was 1992. But that was very, very exciting physics. There's what it looked like. For example, you may not have seen a curve like this yet, but in science we're very interested in the difference between the model and the evidence. The green squares there, are the actual evidence. The red line is not some, it's not like joining the dots like in the creche or something. The red line is the model. So you look how well the green squares actually fit onto the red line. That's an astonishing fit. And that convinced absolutely everybody. Good God. Whatever this model is, it's absolutely perfect fit for what the evidence is. So that was pretty much the end of the Big Bang debate. By then, everybody was convinced this is right. With the perfect black body spectrum, there's extremely good agreement between theory and experiment. One interesting thing about it is not to do with this spectrum here, but going back to that thing, when you look carefully at the thing up there, the distribution isn't quite uniform. And of course, that's what we expect. The reason is because we haven't talked yet about how galaxies form, and that's a different thing. Because obviously space isn't quite uniform, it can't be, otherwise it wouldn't have galaxies. Most of it's empty space, and then you suddenly have a galaxy, and then it's empty space again. And that's right, and that's what we expect. So, last thing, nowadays it might look like science fiction, but believe it or not, that's up at the moment. That's the WMAP satellite. It's launched by NASA in 2002, and what it's doing is doing even more accurate measurements of the same thing. The picture is now beginning to look like over here on the right. Again, we're just looking at the radiation. This is the real live radiation from the Big Bang. Extremely detailed evidence for the Big Bang. Also, evidence coming out of the universe is flat. And even more interestingly, evidence for what we call inflation. I'm not going to go on about this, but one thing that has changed in theory in the last 20 years is it's thought, when the thing began, looking at the beginning, what actually happened was there's a thing called a hyper-expansion, that the universe first expanded very, very quickly at first, and then settled down. And that explains there's a few little problems with the model that people have been wondering about, and that's a very simple explanation. So that's about it. That suits that data very well. It also hangs together very well. And then, unfortunately, just in the last few years again, somebody, as always in science, made a measurement, and they found a result so surprising, it has caused everybody to go right back to the drawing board. Does anybody know what the discovery was, by the way? Something about the expansion of the universe that was discovered? Anybody know what it was? It's always the way in science. You go to confirm one thing and you discover some bloody new thing turns up. And I'm sure all the PhD students were going, oh, for God's sake, I just want to get this PhD finished. I don't care. They discovered something that nobody was expecting. Anybody know what it is? It's the second, well, I said 1929 was the most important discovery of the 20th century. And it was. But now we've discovered something already in the 21st century, though in fact it was just before the 21st century, that turns everything on its head all over again. And it's this. It turns out the universe isn't just expanding. Let me tell you the story the way it happened. In 1998, they were making measurements of a supernova, which is just a very big star which suddenly blows up. They made measurements of the stars moving away, just like, do you remember the old Hubble graph? Only this time they found, bloody hell, the stars are actually moving too fast. So of course everybody said, no, you're wrong, don't be stupid, go and make your measurements again. 3 or 4 different groups all around the world, all the best astro groups there were, all jumped on this, decided to prove them wrong, and they found, bloody hell, they are. The stars are moving too fast, and what that means is the expansion of our universe is speeding up. It's not just expanding. Everyone assumed it was expanding at a nice constant rate, because that's what the graph looked like. Now we know that it's actually speeding up. And that, at first, made absolutely no sense. And then people began to realize, well, in fact, it is compatible with inflation. We don't know why it's speeding up, but that's okay. We're not really that sure why it's expanding in the first place. We certainly don't know why it's speeding up, but it's not completely against all the theory. So there we go. That's pretty much all we know about the Big Bang. Just to show for the next generation, that's you lot coming along, what you will have to face, the problems that people my age are getting too old to do now is, the first one is, what the hell is going on with the acceleration of the universe? We could understand maybe it's expanding, but the fact that it's expanding faster all the time, there's no obvious physical reason for that. I mean, it might be there's a universe somewhere else trying to pull it in or something crazy like that, but that's the sort of thinking we need. Secondly, we still have the problem of we don't really know what happens at time zero, and you might know, apart from relativity, the other big discovery in physics was this thing called quantum. And quantum physics is about the physics of the very small, and quantum physics is very uncertain by nature, and that's the whole problem with time zero. We don't actually know how energy can come from nothing at time zero because we don't have a good theory for things. Time zero involves things that are smaller than the nucleus, and we don't have a good theory for modeling that. And finally, one little thing there, we also think a lot of the matter that's in the universe we can't see. We know it's there because of its gravitational effect, but we actually can't see it. The density is too low. So that's basically the story. And just again, in terms of a summary, let's have a look at this nice picture. This is what we think we know, is probably the best way of putting it. Looking at the beginning, if you see the big white flash there at the beginning, that's what we call the quantum era. We still quite don't know how it began, but we think something pretty much appeared out of nowhere in a quantum way, the way things happen in quantum physics. Inflation got hold of it and blew it up like a balloon as quickly as you can imagine. Before you know where you are, you suddenly have this afterglow, which is what happens when atoms begin to form. Because when atoms begin to form, the light no longer gets scattered and it begins to sort of it begins to travel. So when we look at the background radiation, we're looking at this period here. Then we have what we call the dark ages, which is the interval between those atoms finally get around to forming into stars and planets. Well, sorry, I should say the galaxies and the planets come a little bit later on here. And then basically the universe just quietly expands. And then, unfortunately, right at the end, something unexpected starts to happen. The expansion suddenly starts to accelerate. If you see in newspapers and magazines, by the way, they call that dark energy. And the idea is that some sort of energy, some mysterious sort of energy, is causing it to expand. And there's a little WMF satellite out there that's going on. And of course, the time frame for this is about 30.7 billion. Just before I finish up, I'll just say a note of thank you to the cast. Here are the people who are all important. First of all, the mathematician, Johannes Kepler, who, by the way, was, you'd be amazed how many people these guys were priests. He was a canon in the Polish church. He was the first person to work out what the orbits of planets were. Then Newton came along, who certainly wasn't a religious man, and he came along with the law of gravity. Then Einstein had a new theory of gravity. Friedman applied that to the universe. None of this really interested anybody until Hubble discovered in the 40s, the 1940s, that the universe was expanding. Another priest came along, George Lemaitre, and pointed out, well, my God, if the universe is expanding now, it must have been contracting in the past. If we go back in the past, it contracts, and maybe it originally began as a sort of a point, and that's the Big Bang model. From then on, we just have predictions. We have predictions from George Gamow and his group of the fact that there would be background radiation, and also the compositions of the elements, and so on and so forth. These were then measured in the 1960s. Most people don't believe a word of it, but they were measured in the 1960s. And the same thing happened again in the 1980s when somebody developed a new model of the DD. And again, next thing they started measuring